we do know how we can get data and look at the output of the neural network. We do know how we can compute the gradient, and so we can train our neural network right now. Now let's take a look at one particular example, the very first example, which is the example of doing classification on a data set. Okay? So this image, do you know what is this guy? MNIST, right? So we're gonna talk about that as well. MNIST is a data set containing handwritten digits, right? So they went to the schools, kids wrote down handwritten digits, 0 to 9. They collected them. Okay, this is 0. They're gonna label it as 0. This is 1. They label it as 1, right? And they collected 60,000 of them. Okay, 60,000, 1,000 of each digit, right? 1,000 zeros, 1,000 ones, and so on. And you have it. Simply, you can just load it directly from PyTorch or Torch Vision, and you have access to those samples, right? So every sample is one image, which is 28 by 28, gray image, so only 784 pixels. And then it has its own label, right? And the task that you have is that you give this image to a neural network. At the output of the neural network, it tells you what is the class of this image, whether it is digit 0, 1, till 9. Okay? 10 different classes. So this is image classification problem. Now what we are going to do, we are going to start with the binary classification. So we don't want to do yet multi-class classification. We want to talk about binary classification, meaning that we are not thinking about classifying 0, 1 till 9. We want to know whether the image is image of handwritten 2 or not. Okay? It's a binary classification, right? So the image goes to the neural network. The neural network is going to give you one binary output. And that binary output is going to tell you whether this image is 2, digit 2, or not. Okay? Cool? So this is a binary classification, and the data set is going to look like this. So what are the guys inside this data set? So we have B different samples. These are the number of samples we have inside our MNIST data set, right? And then what is X? The image, the vector of pixels, right? What is V? The label, right? Which is going to be yes or no, as your friend said, right? So V is going to be, so X is the pixel vector, B is the size of the data set, and V is either 0 or 1, right? It's 0 when the image is not handwritten 2. It's going to be 1 if the image is the image of a handwritten digit 2, right? So this is the kind of data set that you have, and we can put one neural network to just do this job, right? And what should be, I want to just consider a deep neural network, and this like the simplest deep neural network that I can think of. So how many hidden layers do I need? 2, right? So I need to have at least 2 hidden layers. So I'm going to take depth 3, 2 hidden layers. This is one hyperparameter, right? Then I need, what is next? What do I need to just specify in this neural network to be able to implement it? The number of neurons in every single hidden layer. So the width, say I put K to be the width of the first layer, J to be the width of the second layer, okay, hidden layer. Okay, so the input goes to K different neurons, right? Again, the output of those neurons go to J different other neurons in the next layer, and then that guy is going to compute the output for me, right? So this is the way that I'm going to do. I'm going to use for activation ReLU function. So every single neuron in the hidden layer is just activated by the ReLU function. So any values go inside these neurons. If it's positive, it's going to pass. If it's negative, it's going to turn to 0, right? Everybody's cool? OK. I'm going to show it by R just to simplify the whole notation. That's it. And for the output, at the very end, what I want to do, I want to classify it as a 0 or 1, right? I want to say whether this is 2 or not. So I need the output to be a perceptron, right? So I'm going to put the output to be a perceptron. That very last guy is a perceptron, looking at everything coming from the last hidden layer. And then it's going to compute one value, which is either 0 or 1, right? A soft information z, and then pass it through the step function. Everybody's cool? Questions? So this is a kind of valid model because it's taking my image, it's turning it into 0 or 1. This is what I want, right? And the only thing that I need to do is to just, so this is my model, right? It's going to get my input, and then it's going to pass it through these two layers, and finally it's going to give me one output. That output is either 0 or 1. This is exactly what I want to do in this binary classification, right? Everybody's cool? Questions? No question? OK. Now, if you want to think about this one, you can simply write down the learnable parameters, for example. What are the learnable parameters here? So these are the weights that are showing up in every single connection, right? So the weights here plus the biases of these neurons against the weights here plus the biases of these neurons, and the weights of the very last perceptron, all of them are learnable, right? So you can update all of these guys, right? So if I want to count the number of learnable parameters, how can I do it? Well, I could say if I have n different inputs, so I'm going to have n times k different weights, k different biases for that first hidden layer. So yeah, this is going to be the number of weights I have in the first layer. The number of weights I have in the second layer, well, k goes to j. So it's going to be k, j different weights, and j different biases. Again, you can write it down in this form, right? What about the very last layer? How many weights does it have? J plus 1, right? J plus 1, so the last layer is going to have j plus 1. These are the weights plus the bias of the last perceptron, right? So you have this much. So you can say that I have this first number plus the second number plus the third number. This is the number of parameters I have in this model, right? So my loss function, my loss value, is going to be a function of all of these weights, right? And I compute the gradient with respect to all of them, right? Everybody's cool, right? OK, so you can think of it in this form as we did before. So instead of biases, we're going to put a bunch of ones here, right? And these ones are, I mean, the weights of these blue links are essentially the biases that we have, right? So we can forget about the bias itself. We can think of it as a weight. This is what you always do on PyTorch, right? You don't specify, you just write linear layer, this dimension, bias, true or false, right? That's it. So now, what about the loss? If you remember, when we started with the perceptron, we used this loss, right? This was the loss we used in the perceptron machine. And given the current last layer, last perceptron that we have, this is a kind of good choice for the loss, right? What is the loss here? So I'm going to look at the output of the perceptron. This y is the output of the perceptron. And I'm going to compare it to the true label. The true label is either 0 or 1. This y is, again, 0 or 1. If they are the same, I'm going to say I have no error. If they are different, I'm going to say that I have error, right? So that's it. So this is my activation. And once I have the activation, we can just do the forward pass and backward pass to compute the gradient and do the update, right? If you remember when we started with the perceptron machine, I told you that choosing this loss or choosing that step function for the last perceptron, they are bad choices, right? Everybody's clear? Everybody recalls that? OK. I told you they are bad choices. And now, since you do know what is backpropagation, you clearly see why they are bad choices. OK? So let's take a look at this together. I am not going, I mean, I used to be very bad person, and I just do it step by step for the student. I'm not going to do this. I keep it in the slides if you are interested to see how the forward pass and backward pass exactly look like on this architecture. You can do it, but eventually you just need to write down the computation graph, right? Your data goes in, first Z activated, second Z activated, last Z activated, and you have the loss. And you can start writing down all of these things, right? So I believe that you all do know it, right? So I'm not going to be very obsessed with that. And the key thing is that at the very, very end here, when you want to compute y, you're going to use in a step function, right? So whatever the z value is, you're going to look at the sign and you're going to give it 0 or 1, right? And you can go ahead and write down the gradient descent algorithm, this is going to be the algorithm that is going to update your weights. So the weights of the first, second, and the output layer are going to be updated in this form, right? Learning rate minus the gradient, right? And the gradient, you write it down as the average of those sample gradients, exactly like what we had in the gradient descent algorithm. But the key point here is that you should be able to just back propagate, right? Line 5. If you want to compute those sample gradients, this means that when you put one single image to this neural network, this image should go forward, compute the last output, and then you should be able to compute the gradient of the loss with respect to all the weights, right? Essentially with respect to all variables in between, right? Between your input and output, right? So you need to do that, and you can keep on going like this. So again, I am going to drop this part because this is just simple forward propagation that we did. Once you do the forward propagation, you get all these variables, right? Data computes the first soft information activated, second soft information activated, last soft information activated. This is your output, right? And you can write down the forward pass, right? This is going to be the forward pass. Once you have the forward pass, then you need to just move backward, right? Now, if you want to move backward, what do you do by backpropagation? You start with the loss here, right? And the first thing, you're going to move backwards here, right? It's going to be the derivative of the loss, right? Then from this one, you're going to take the derivative of your activation. You keep doing linear operation, derivative of activation, linear operation, and so on. Now, here, in this graph, do you see anywhere a problem that might stop you from computing gradient? Derivative of the loss function, right? This loss was crazy. So it's going to look at two values. It's going to give 1 or 0, right? What is the derivative of that guy? You cannot really write it down, right? And you can try to intuitively define it, but at the end of the day, this guy could be 0 in very places, right? And wherever it's 0, it is start to be 0. All the gradients after that are going to be 0, right? No gradient is passing backward. No update is going to happen on your neural network, right? Same thing for this step function. What about this step function? The step function is 0 jumping up 1, right? If you really want to write down the gradient, it's going to be only infinite at 0, right? Anywhere else, it's 0, right? And this means that this guy is also breaking the whole chain, right? It's stopping gradients from moving backward, right? This is why we are not interested in such weird functions in our neural network. Because when we are moving backward, we get trouble with the gradient, right? These guys are stopping us most of the time. Even if you come up with some tiny, say, for example, instead of this very step function, you just consider a very tiny slope between 0 and 1, right? You just shift it and make a very tiny, very harsh slope in a tiny interval. It's going to give you gradient only in this interval, right? Anywhere outside this interval is going to give you no gradient, right? And when you have no gradient, 0 here going to make every other gradient in this whole computation graph 0. That particular sample is giving you no update, right? So your weights are not getting updated when you use gradient descent, right? So the gradient is the key, the key component that is updating our neural network. And if we don't have it, we don't have any update, right? We don't know what to do with the weights. Weights are going to remain the same, right? And this is why we're not interested in this. So you can start writing down the gradients. So you're going to see that these two particular derivatives, the derivative of this weird error indicator function and the derivative of this step function, these are the guys which are going to make the whole trouble, right? So most of the time, they are going to stop us from having a gradient. The gradient is simply 0. So again, I'm going to jump this part. So you can go ahead, write it down. This is exactly the same thing that we did today. So I don't want to just tire you with this whole story once again. Now, the key point that is going to be the challenge is these two guys, right? The gradient of the loss, the derivative of the loss, and the derivative of the step function, right? So these two guys are making us trouble. We don't have them. We cannot move backward. Now, do you have any idea how we can get rid of the issue with this maybe we start first with this step function. Do you have any suggestion? How can I make this a step function? You suggest sigmoid, right? Why you suggest sigmoid? It looks the same pretty much, right? But it's a smooth, right? And it doesn't matter what the value of input is, right? It always has a gradient, right? So what was the expression for sigmoid function? It was 1 over 1 plus e to power x, minus x, right? Now, this guy, it doesn't matter what the value of x is, right? Always you have a derivative, right? When x is very large or very small, like if you go to plus minus infinity, the derivative is going to be small, but it's still not 0, right? When you are closer to 0, the derivative gets larger, right? So it's going to have derivative. Maybe we can just come up with that one. So we need a smooth function. We just need to replace this step function with a smooth function. And sigmoid sounds like a very good choice, right? So yeah, this is the sigmoid function, right? This is the sigmoid function. This is the expression that it has. It is somehow mimicking smoothly what this step function does, right? It's just starting from 0, going up to 1, roughly. But it has this good property that it has always gradient, right? And this means that I don't need to care about what the output is. Always when I move backward, I'm going to have a gradient, right? The gradient is not 0. I can always update my weights, right? Cool, right? So let's just do this. So let's just use sigmoid function to just get rid of this issue that this step function is not differentiable. So we're going to replace it with one differentiable function. So this means that I am going to have my first hidden layer, second hidden layer, then it goes to one neuron. That neuron is no more a perceptron, right? It is activated by sigmoid. And the output of that sigmoid is a number between 0 and 1, right? But now it's a new challenge. The challenge is that this output is not necessarily 0 or 1. Actually, it's never 0 or 1, right? It could be any number between 0 and 1, right? And now the question is how I can use this in order to compare it to what the true output is, right? Because the true output is either 0 or 1. The label that I have inside my data set is 0 or 1, right? My image is either handwritten 2 or not, right? How can I compare these two? Any idea? How can I map this value between 0 and 1 into, or compare it with the true label, which is 0 or 1? Yeah, if it is 0.9, what do you think? What do you take it? As 1, right? If it is close to 0, is 0.1, you're going to take it as 0, right? Probably in your mind, you're going to set one threshold half, right? You would say any value above half, I'm going to treat it as 1. Any value below half, I'm going to treat it as 0. If you think like that, you are thinking probabilistic, right? What you say, you would say this output that I am computing with my sigmoid is essentially the chance, the probability of that image being 0 or being 1, right? This is the image of the label being 1. When the value, the probability of the image being 1, right? When this probability is close to 1, then I'm going to take it as 1. Essentially, when it's more than half, I'm going to say that the higher chance is that this image is, the label is 1, right? When the value is below half, you say the higher chance is that the label is 0, so I'm going to take it as 0, right? Okay? So this is how you can interpret this. So this is the you treat the output as a probability, and then once you have the output as a probability, then you have this chance to look at the output and compare it with the label. Now, one question here is then how you can compute the loss. Because when we were talking about the loss, we put this indicator function, right? We said when the true label and the label that we have inferred in this neural network are the same, then we are going to say no error, but if they are different, we are going to take an error, right? So now we don't have this property anymore, right? Because the output is something between 0 or 1, right? Now, if I interpret that 0 or 1 as 0, value between 0 and 1 as a 0 or 1, right? So if I say like after half, more than half, I'm going to take it as 1. Still, if I compare this inferred label with the true label using the indicator loss that we talked about, we're going to still have problem with training, right? Because the indicator loss has no gradient, right? So I still cannot really do this, right? This is not a good idea that I keep the loss as before. So I need to somehow come up with better idea. Any suggestion? How can I do this? Yeah? Exactly. But why 1? Why 1? The sigmoid is between 0 and 1, right? When the true label is 1, what do you want? No. What do you want for the output? How should the output look like? 1. Close to 1. I mean, it never gets 1. You want it to be close to 1, right? When it's 0, what do you want? Close to 0, right? So if you compute instead of the indicator, you compute the difference between y and the true label. Right? Take a square of it. It still does the job for you, right? Sorry? Yeah, you have just one label, right? Your label is a scalar right now, right? Only one, right? So you need to replace that loss, and you can replace that loss to just mimic what you want, right? So this is going to be the idea. Now, what you can say that your true output that you have, the true label that you have, V, okay? This guy is either 0 or 1, right? And you can again interpret this as a probability. When V is 1, the label is 1. You're going to say the label is 1 with probability 1, right? When V is 0, the label is 0. So the label is 1 with probability 0. So you can say that the true label is actually, whatever you see V as the label in your data set, is the true label is 1 with probability V, right? So you can interpret it the same way, and you could say that, okay, V is a probability of being 1, the very true probability. Output of my neural network is the probability that my neural network has computed. And now I only need to compare these two things, right? And then I can compare them with any nice loss function, which is actually having derivative, right? So you can do this as well. So you could say that the V, which I have inside my data set, is the probability that the true label is 1. Whatever I compute by my neural network is again the probability of being 1. And the thing that you need to do is to just compare these two different values, right? Now, definitely the thing that you don't want to do, you don't want to compare them by the indicator function. We talked about it. It doesn't have derivative, right? And the other thing is that, like, yeah, here is a dummy argument, but even if you wanted to do that, you couldn't really do it because the sigmoid function would never give you exactly 1 or 0, right? You need to hard threshold it again, which is making the whole trouble once again. So you definitely are not going to use the indicator function. You can use any function which just makes these two values as close as possible to each other, right? One thing that you can use is this one, right? The mean squared error, right? If V is 1, then Y is going to get close to 1 to make the error minimum, right? And if V is 0, then Y gets close to 0, right? And this is going to lead you to the right classification, right? So this is going to work, right? Now, anyone knows what we use in practice? Anyone has heard of anything we use in practice instead of this guy? If you use this one, you're using MSE as your loss function, right? But most of you might have heard when you want to do classification, you usually use cross-entropy, right? And what is the cross-entropy? Well, I'm going to explain it next. So this guy is not a bad guy, right? This is computing the loss that you want. You can take the derivative, so it's a very nice guy. You're going to have the derivative when you are moving backward. Everything is fine. But this is not the best guy you can get, right? A better guy that you could have is what we call it the cross-entropy. So what is the cross-entropy? So everybody just looks here. Cross-entropy is very simple. You don't really need to confuse yourself. So when I have this y3 being, if my true label is 1, right? My true label is 1. What do I want for y3? I want y3 to be 1, right? Now, I'm going to compute log of 1 over y3, okay? If v equals to 1, I'm going to set the loss to be a log of 1 over y3. Now, if y3 gets close to 0, to 1, what's going to happen? What's going to happen to the loss value? It's going to be 0, right? If y3 is very small, if it gets close to 0, what's going to happen to that loss value? 1 over 0 is infinite. Log of infinite is infinite. It's going to get very large, right? So if y is close to the label that I want, is going to be 0. The loss is going to be 0. Once I deviate from that value, when I get close to 0, which I don't want, the loss is getting infinitely large, right? Now, if v equals by 0, then instead of y, I'm going to replace in the denominator 1 minus y, which is again the probability of v being 0, right? When y is the probability of v being 1, the true label being 1, the 1 minus y is going to be the probability of label being 0, right? Again, if y is close to 0, then denominator is close to 1. This loss is close to 0. If y is close to 1, the denominator is going to be close to 0. The loss is hugely large, right? So what is happening is that, again, this guy is taking your y where you want, but when your y is not there, it's getting hugely large, right? And this is going to penalize your whole mistake much larger. It's going to give you a larger gradient, right? And this is going to help you train your neural network faster, better, right? This is what we call it cross-entropy. People write it down in this form, okay? But you don't really need to confuse yourself. Just replace v equal by 1. Then this guy is going to disappear. It's going to be minus log of y3, which is exactly the first term, log 1 over y3. You just set v to be 0. The first term going to get 0. The second term going to be minus log of 1 minus y3, which is the second term in the condition. When you compute cross-entropy is always log of probability of your class minus, right? Or log of 1 over the probability of your class. And the key point about this loss function is that, first of all, it has the gradient. You simply can compute the gradient, same as the MSE. And the other thing is that it is doing much harsher sort of penalizing. So if you, for instance, think about your label being 1, if you use MSE, your loss starts from 1, goes to 0, right? But if you use cross-entropy, it's going to start from very, very large value and goes to 0, right? Meaning that it's just going to push or give you a higher penalty. When you compute the loss, it's going to give you a faster boost towards the right output, right? Same thing going to happen if you have the different label, right? So cross-entropy is essentially doing the same thing that the MSE does intuitively, but it's doing it with a larger or harsher penalty, or in terms of backpropagation, it's doing it with larger gradients, okay?